So yesterday we looked at, again, the notion of Lie algebra. So first we define it quite abstractly, just saying, okay, it's a vector space with this binary operation satisfying some properties, so meaning what are the properties? So the antisymmetry of the Lie bracket and the Jacobi identity. So this define what we call Lie algebra. But then in physics usually it's not very useful to only have this quite abstract definition, and it's nice to know how elements of this Lie algebra are going to act on a given vector space. So that's why we needed to introduce this notion of representation, how to represent a Lie algebra. And so what we've seen is that any Lie algebra has at least one representation, which is the adjoint representation. Okay, so this is what we said yesterday. And then during the tutorial, so I don't know, I think some of you had time to look at the second part of the tutorial. The question was try to build all irreducible representation of the algebra SU2, the Lie algebra SU2. Okay, so now we're going to look at a specific example. So we're going to look at SU2. So of course you already know that for SU2 you could have the adjoint representation of SU2, but now we want to find all irreducible representation. And so first maybe I should remind you, I gave you the definition of irreducible representation in the case of a group. So it's quite similar in the case of algebra, but let's give me your definition. Okay. So first, what is irreducible representation for a Lie algebra? So yeah, first maybe I should specify that usually, at least in the physics literature, we are most of the time using the term representation for also instead of representation space. Okay, so also for the vector space on which we represent things, we also call that the representation. And so yeah, it's a slight abuse of terminology, but it's what we're going in all physics books or all physics articles. Most of the time when we talk about representation for algebra, in fact, we talked about the representation space, okay? And indeed, when we define an irreducible representation of a Lie algebra, in fact, we talk about the representation space. So we want that the representation space here, so the vector space, does not contain any non-trivial invariant subspace. So it's quite similar to what you had in the group case. And by invariant subspace, what do I mean? An invariant subspace U of a vector space is, so of course we need to specify for a given map or a given representation. So it's when it's mapped into itself, okay, by all representation of all elements of X. So this means that, what does it mean? Acting on any element of U is still an element of U, okay? And this for any here X in the Lie algebra. Any X, sorry. Here, I'm not talking about the algebra yet, so it's a vector space V. Okay, so this is what we call irreducible representation. So now let's look at what you had to do yesterday in the tutorial. Okay? So the starting point, now we want to focus on this specific case. And the starting point, again, we have seen that we can characterize completely Lie algebra once we know the Lie bracket and the constant, structure constant. Okay? So we know that this is our starting point for SU2, where here SU2 is a compact, okay, SU2 as a group is a compact group, and so indeed here we have seen yesterday when we are dealing with compact, in the compact case, then the constant structure is totally antisymmetric. And what is the most simple totally antisymmetric tensor is this epsilon ABC. So this is really the simplest non-trivial case of a Lie algebra we can start with. And we will see that, in fact, SU2 is quite also important, because then we can use SU2 to really generalize that to more SUN, and then to try to classify a bit Lie algebras. Okay? So this example is quite important. And in addition, the method we are going to use to build up all irreducible representation here is quite general, can be used for different groups. Okay, so what was the first step? The step one was given to you, okay, was to find what is called the Cartan subalgebra, meaning you need to find the maximal set of mutually commuting operators. Okay, and here in the case of, so here, yeah, SU2 I forgot to specify, yeah, it's three-dimensional, as a vector space, it's three-dimensional, okay, and indeed here we have three generators, the GA, where the indices here A, B, C, so you can take the value 1, 2, 3, or sometimes you find the notation X, Y, Z, okay, depending on. So here, for the Cartan subalgebra, in the case of SU2, we only have one. We can, in fact, choose only one of these three generators. So usually, we choose, in the literature, is it J3, which is chosen. So we are going to do the same here. And then the second step was to find the eigenvector of the commutator operator, okay, with this J3. So to find if this is an operator, what are the eigenvectors here? So this means you want to find an operator, J, that has, when you take the commutation with J3, what you get is a constant time this new J. And this J, so I ask you to start with a linear combination of J1 and J2. And so what did you get here? What are those?
Alpha equals plus minus I.
Yeah, so here we got two eigenvectors, J plus J minus, that we're going to call the lowering. And so it's J1 plus or minus I, J2. And then usually we are going to normalize this in a specific way. So here I'm introducing, of course, the normalization. Here you cannot get it from this commutation relation. It's just given to you. Okay, so these are our two eigenvectors. Then the second question was, of course, from here you can compute explicitly what are the commutators, okay, between J plus minus J3 and. So this was just a direct calculation, and of course you find here that the numbers you get here are the eigenvalues of your vector, or if you want, the weight we're going to see. And here, what do we get? We get just J3. Then, so this was the second step, okay, to define. So here, what we get is the raising and lowering operators, and they appear here as eigenvector of this commutator operator here. Okay? So then the third step, which is the longer one, is to define build the vector space. Okay? Using here the highest weight method. So here we want to find the vector space of, it can be dimension. The dimension of the vector space here doesn't have to be related at all to the dimension of the Lie algebra again. You remember that when both are equal, this means that you are talking about the adjoint representation. Okay? But we will see that, in fact, you have many more representations, and the dimension of the representation won't be at all the representation of the Lie algebra here. And what we are going to use is what we call the Okay, so what was the first question for you? Yeah, so the starting point is to start with some vector eigenvector for this J3 operator, okay, where here M is just a number. For the moment, we don't have any condition on this. So this is, we're going to start with that. And now we are going to, what happens if we act with J plus minus on this state? And here using what you get here, so here the idea was to use the commutation relation between J3 and J plus minus. What you get is that as a result, you find that here you get if we compute that using introducing here this commutator. So what does it mean here? This means that this vector is, of course, an eigenvector for J3, and here we have the value of this M here. So this means that this is proportional to the vector M plus or minus 1. Okay?
Sorry, on the left-hand side, should the J3 and the J plus and minus be the other way around?
Sorry?
On the left-hand side of that, should the J3 and the J plus and minus be the other
Shouldn't
way?
J3 act on J plus minus M?
Yeah, because only that way we get.
Oh, yeah. Sorry.
Otherwise, it's 10.
Yeah, so you look at this. Yeah, very good. So what does it mean here? This means that now starting with starting with state M, we can go up or down using the raising or lowering operator between states. So in particular, what do you have? So you start with something like this, and then acting on J plus, you will go to plus 2, etc. And now if you act the other way, yeah, then here you're acting with the lowering operator, you get this relation. Okay, but here we are going to focus. So this means that this looks like it's infinite. But first, let's focus on finite dimensional representation. Okay, so this means that we want this to end at some point. So let's focus on and so we are going to define this means that we can have highest weight that we're going to call J. And so how is that defined? This means that the action of the raising operator on J has to be 0. So what does it mean? Because we also calculated just right now that J plus on J would be proportional to J plus 1. So this means here that we must have a coefficient equal to 0. So now let's try to figure out so we know what is the coefficient in this case for the specific value when m is equal to j. But now what is this coefficient? So in fact, these are going to give you the matrix element of your representation. What are the matrix elements of your representation for any m? And what are the valid value of m and j? Okay, these are the two questions here we have. And of course, we're going to, so here it seems that m can be has to be smaller than j, but do we have another condition? For example, do we have a lowest limit? And then what are the values that the j can take? Okay? So so here with our vector basis, let's require that this vector basis is normalized, is orthogonal, so that we have this relation, okay? And so how do we define? Now we are going to define the matrix element of this lowering operator with this coefficient, depending on this m component. And so now the question you had in the tutorial was to find a recursion relation, okay, for this coefficient here that you have here. So these coefficients are going to be your matrix element of your j plus and j minus operators. So how do we get this recursion relation? So here the idea is to use the commutator between j plus and j minus, of course. But first we need to find a relation to find if there is a relation between the coefficient. So is it a completely different coefficient here that we have, this n? Or do we have a relation between these two coefficients here, okay? So here we need to use the fact that these two are Hermitian operator, okay? Adjoint conjugate. So what does it mean? So let's look at here. So what do we have here? This nm is equal to the matrix element of the lowering operator between the state m minus 1 and m, okay, using this relation that we have here. And here we're going to make the assumption that these coefficients are real, okay, a real parameter. And so using the fact, now we can take the adjoint of that. So what do you get here? This is also equal to so from this you can deduce that the action of j plus on m minus 1, since you have the matrix element here, is, so here we use the fact that dagger is equal to j plus, okay? And so what does it mean? This means that j plus on the vector m is n okay, very good. So now that we have this, we can really define. So now if I look at the commutator and at the matrix element of this commutator, I'm going to get a recursion relation which is going to give me a definition of this n coefficient. Okay, so here we know that J plus with J minus is J3. Okay, and so J3 will give you M. Maybe I should write the step. So this is also J3 MM, and this is equal to M. But now we can also use the fact that this is also equal to J plus J minus minus J minus J plus, and we want to look at the matrix element of this combination. So the action of J plus on M will give a M plus 1 with a N M plus 1, and then the action of G minus on M plus 1 will give N M plus 1, and you get back to M. Okay? So here, from this term, you get square, and from this one, you will get just. So this was part of the tutorial, so I guess, I don't know if many of you had time to look at this. Try to do it by yourself, but yeah, this is quite straightforward. So here you see that we get this new relation, recursion relation between this coefficient. So we get that and here so this is our recursion relation. We already have a initial condition. So what is the initial condition that we have here? Which one do you know?
J.
And of which one is equal to 0?
J equals
J or J plus 1?
J plus 1.
Yeah. Okay. J plus on J is equal to 0, but it's also equal to N J plus 1. Okay? Very good. So starting with that and this, so then, for example, you can try, and so what do you get? We get that the N, this one is 0, so this implies that M of J is square root of J, etc. So you can go step by step and obtain all the expression and try to guess what is the final an expression for any M here. Or you could also use Mathematica, I don't know if you have that, and then use the command R solve, and you will get a nice answer which gives you that the solution to this recursion relation with this initial condition is and so what do you see here? That this indeed is going to vanish when M is equal to J plus 1. But this is also going to vanish for another value. Which value of M? Yeah. So we also have that N of minus J here is equal to 0. So what does it mean? This means that here the action of the lower operator on minus J is equal to 0. So this means that here, without any more assumption, we get that we have a lowest state. Okay? So we didn't assume that this was existing. So here, and this is good because, as we said, we wanted to have a finite dimensional representation. So we just assume at some point that we had the limit, upper limit, but then automatically we get the lower limit. Okay. So.
Sorry. So why does that mean that it's not in the representation?
Sorry?
Why does the fact that J minus annihilates minus J state, why does that mean that it's not in the representation?
So no, the minus J is part of the representation, but it's the lowest.
I mean, why does it mean that minus J minus 1 is not in the representation?
No, it just means that, so you see that here, so we start with our, we want to see how many vectors we have in our representation, okay? And you see that, so here, if we start with, so we started with this one, okay? And then you see that, in fact, you could do, how many steps can we do? You can start from, so this is the lowest weight, and then you can, so yeah, during J minus, you can do 2 J steps, in fact, to arrive to minus J, and then you end up again on the 0 mode. So you don't have any more, you don't have any other vector here, okay?
But I'm wondering why it is that you know that because you can't reach it with the ladder operator, that means that it's not in the representation.
Yeah, rigorously.
Yeah, I don't really see what you mean by not a representation. It's not part of, in fact, what is the representation? The representation state is all this set of vectors. It's just that we need to find how to characterize this vector. So we have a vector space, and we need to characterize this vector space, and we see that assuming that this vector space has a finite dimension, okay? So we said that we can pick up, since we have this property, also we found that we have this property on this J plus and J minus operator, meaning that we can call them raising and lowering operator. Yeah. Okay, so then we can say, okay, so let's start with the highest way, and then you will be able to get all the vector using the lowering operator. And at the end, you figure out that you end up at a last vector, because then when you act with that, then it's a 0. So 0 is part of your vector space, of course, but then you don't have any other vector. Okay, so it ends up there.
But why do you assume that you can get to all the vectors using the ladder operators?
Yeah.
So these are your generators, okay, of your. So I can say it differently. So
I think she's shown it up there was J3 acting on the state gives you like the state number, and if it gives you 0, then it just doesn't exist. Like
yeah, so it's just so we start we have picked up one here, one generator which is preferred, which is J3. Okay, so we know that we can find a vector basis for this state. So we start from that. Okay, and so here at this stage, when I wrote this, it seems that we have an infinite number of states. Okay, and so now I'm just going to. So we want to. Here we are looking at the representation of this algebra. Okay, so it doesn't mean. So we want to see how, as operator, they are represented on a vector space. Okay, and so we first need to define what is this vector space associated to this operator. And here you see that we only have, so we're starting with all the eigenvector for J3, and now we see acting with the other operator what condition we get. Okay, so we only have, so here we used all the operators. Okay, so, and we are only interested in the representation of this operator. So it doesn't mean that. So for these 3 operators, then they're only living in this vector space. Okay.
But does that always imply that we don't have more? Like, for example, if we were working in something that's not connected, like a non-connected space, probably that wouldn't imply that there could be other.
But then you, even at the level of the generator, you will have something a bit more, I guess, more complicated. Because here, what makes also things so simple is that the Cartan subalgebra is given by one vector. Okay, so we have only one parameter here. Okay, we have this M, which characterizes this eigenvector of this J3. Okay. So then, for a not connected, in the not connected case, but usually the Lie algebra, because then it's more about the group that you talk about, connected or not connected. And of course, so here, these are going to be, we are going to find some representation. And these representations are going to be the representation of the group SU2, because the group SU2 is simply connected. But for example, this, you know that the SU2 algebra is also the Lie algebra for SO3, but SO3 is not simply connected. And indeed, these representations that we are going to get are not going to be all the representation of SO3. So when you go to the group, indeed, there are some subtleties. Okay, it's not always, you don't have, if the group you're considering is simply connected, then all the representation you have found at the Lie algebra level are going to be the representation of your group. But when it's not simply connected, this is not the case. So for example, for SO3, so here at the end, you see that here we have now two numbers, in fact. We have this J, and we have the M. But in fact, the M is going to be what is going to characterize completely your representation. The label of your representation here is really going to be this J. That, in fact, is what we call the spin in physics. I'm going to come back on that. And so doing all the steps, we're just going to see that. So here already, you see that we have 2J step to go from J to minus J. So this tells you something about J. You want J to be, it has to be a half integer, okay? Integer or half integer. So this means that J has to take the value between 0, 1/2. And indeed, this is, because you want this to be so this is a simplest way to see that J has to be a half integer here. But so indeed, irreducible representations of SU2 are characterized by a half integer, which is called in physics what you are going to call the spin. Okay, but for SO3, you have to be careful. If you look at the representation of the SO3 as a group, then it's not going to be all this spin variable. It's just going to be the integer ones. Okay, so you can just have J equals 0, 1. So it's like you have some, you don't have access to all of them. Okay, so usually when we want to find irreducible representation of a group, it's much easier to work in the Lie algebra. Then, of course, you have to be careful to go from the Lie algebra to the group, and especially if your group is not simply connected. So here, SU2 is simply connected, so that's why quite often, sometimes you mix, you say, oh, I'm talking about the SU2 irreducible representation or the group and mixing, because it's exactly the same, meaning that they are characterized by the same and they are acting on the same vector space, which is going to be given by this vector M, but labeled with this J. Okay? So let's just finish on that. So here, this is an important characteristic. J can take only these values, then what? And M, so for a given J, we have seen that M can go from, so minus J to J. So what is the dimension? How many states do we have here? 2J plus 1, yeah. So here, this is an important number. Sometimes it's denoted DJ. So it's also the dimension of the representation, where again here by representation, in fact, you mean representation space, because this is exactly the number of states that you have, okay? And so now, since we're going to work for given J, now our basis, we're going to use this notation. Where here, again, the M can take this different value. Okay, so here, now if you look at your matrices as a matrix representation of your operator, okay, these are going to be, they are going to be, for a given J, they are going to be represented as 2J plus 1 times and of course you can compute now all, since you have this value here, you can compute all matrix element of your operator. So for example, if we just look at J plus, the matrix element with the indices M prime M is given by and here you get that this is going to be M prime M plus 1. Okay, so this is one of the element matrix. And if I give you a specific example, so for example, you could look at just, so you can write this explicitly in terms of the J and the M, but here if you have just 1/2 minus 1/2, then you get n of 1/2. So you see that here we started with this commutation relation, these 3 generators. Then we did a kind of change of variable. Okay, we introduced it J plus J minus. Of course, here you could also go back to the basis with J1, J2, J3, and define using, because now you have, you know that J1 is and J2 is going to be with an I guess, somewhere. Okay, so you can really also consider this new basis if you want. Okay, so this is what we call so the spin representation of SU2. Okay, and the spin is in fact the highest weight. Okay, in our construction here is this J. This is what we call. So then let's just give you consider some specific value of J, which are important in physics, and see if we can say something. Of course, so when J is equal to 0, then you only have, there is one state, okay? And it's trivial, so often so here you only have one state, and in the physics literature, it's often referred to as the singlet. And in fact, here it's quite trivial as it does not transform under SU2 at all, okay? So this state is not, this case is not very interesting usually. So then the next value that J can take is 1/2. So then in the case J is equal to 1/2, then here you have 2 states that we refer to as a doublet, or in quantum information, in the language of quantum information, you're also going to work with SU2, and it's what you call the qubit. I think this is the spelling. So this is just what you will see in quantum information. You will use both the word cubic. And so since SU2 is defined by, so it's a special unitary 2x2 matrices, okay? SU2 are, here you see that for J is equal to 1/2, the number of states is also the dimension of, is equal to the dimension of the defining matrix of the Lie group. So here we said that the spin 1/2 representation is the so-called fundamental representation of SU2. And so fundamental is when the dimension of the representation is equal to the dimension here of the representation of the matrix representation of the group. Okay, but I'm going to come back on that in the next part. Here it's really, I can already mention that for SU2 because as I said, when we talk about representation of the Lie algebra SU2, it's exactly the same thing as to talk about the representation of the group. Okay, so this is just for some vocabulary, but I'm going to come back more precisely on that. And then just let's look at another case. So here, how many states do we have? So if J is equal to 1, then M can take the value. So here we have 3 states. And it's what we call the triplet, or in quantum information, sometimes we will see the notion of Q trit. Okay, if you're interested in. And here, the number of states, so the dimension of the representation here is equal to the number of generators. So this should sound familiar to you. What does it mean? Yeah, so here, but if you compute explicitly these matrices and you compare with what we had in the previous lecture, you won't find exactly the same matrices. But what does it mean? This means that you can show, and this was, I think, the last question of the tutorial yesterday, you can find a similitary matrix and show that this representation is equivalent. So this means that here, this representation, the spin 1 representation, is what we called equivalent. So I think I already introduced this in one of the first lecture. Okay, and so this was the last question of the tutorial where you could find a matrix S, which is invertible, that has any J can be related to the J of the adjunct representation, okay, if you build different matrices. So here, now you can get all matrix elements, so you can define what are your J in the spin 1 representation explicitly. It's going to be a 3x3 matrix. Then, using what we have done yesterday in the lecture, you can also write explicitly these matrices, which are also 3x3 matrices. And then you can show that you can find S invertible, such as you have this relation between all of them. Okay? So, indeed, they are equivalent. Okay, so any questions here? Okay, so besides here, one important parameter you see is this spin J, and of course this define. Oh, sorry about that. Okay, so I cannot move this one. So this is the dimension of the representation is an important characteristic of the representation here. But we also have another important object. And in fact, in this case, we are going to see that it's going to characterize more or less the same thing, the spin. But this is not going to be always the case, so I want to introduce this now. So another important quantity characterizing the irreducible representation of SU2 here is the eigenvalue of this operator. J squared, which can be just written in terms of the J1, 2, 3 component. But of course, you can also write it in terms of the J plus J minus. So you can see that this operator is not an element of your Lie algebra, okay? But it's because it's it's not linear here in the generators, but it's a well-defined operator which can act on your Lie algebra. So this is a well-defined operator. And now what makes this operator so interesting is that if you compute the commutator of this operator with any of the generators, so it can be in this basis or in this other basis, okay? Then you find that this commute. Yeah, just to come back to this representation here, sorry, the J1, so the spin 1 representation, you see that here, in fact, when we write the matrices, usually we use the plus, minus, and component 3 bases, whereas for the adjoint representation, first already you remember we stayed in the J1, J2, J3 bases. And really what does it mean that they are equivalent? It really means that we are not working in the same basis. Well, the relation here is in fact a bit more, it's not only this change of basis here, it's another change of basis, but it's related to this idea that you choose a different basis to represent your matrices, okay? These are equivalent. Okay, so we have this. So this means that this commute with all generators. And a very important lemma is the Shor lemma that you're going, I guess, to see several times. So what this lemma is going to tell you is that if a matrix commutes with all representation matrices of an irreducible representation, then it must be a multiple of the identity matrix. Then it must be of the identity matrix. And so what does it mean? This means for this operator, this means that this operator is the eigenvalue of this operator is going to be constant on the whole irreducible representation space. Okay, so for a given J, in fact, this is going to be a constant operator, meaning it's just going to be the identity matrix up to some coefficient. Okay, and so in fact, what does it mean? This means that here you can compute just what is this eigenvalue, just for example, using the highest weight or anything, any state, and you will find what is this coefficient the proportionality coefficient that you have here. Okay? And here what we get is that this is j plus 1. And this operator, j squared, is what we call the Casimir operator. And yeah, again, the eigenvalue of the SU2 Casimir. So SU2 has only one Casimir operator, which is this one. So for more complicated than Lie algebra, sometimes you have more Casimir. You don't have only one. Then this gives you and so in fact, if you look in the literature, sometimes to build up the SU2 irreducible representation, you really start by finding what are the Casimir operator, because the Casimir, then you know that it's going to be proportional to the identity, so it's going to be characterized by a number, which here gives you already the spin, okay? And since you have, so in particular, since this is commuting, okay, are commuting, this means that you can diagonalize them simultaneously, okay? So this means that indeed you can work in this kind of basis, where here j is going to be the eigenvector, the eigenvalue of j squared, and m is the eigenvalue of j3. Okay, so sometimes in the literature you first try to find what are the Casimir of your Lie algebra, then it's going to give you some here label for. In fact, it's what is going to give you the label to characterize your irreducible representation. So here you see that it's indeed labeled by the spin. And then since you get your Cartan subalgebra, but since this one is also commuting with all the generator, you know that you can diagonalize them at the same time, and so work directly from that. Okay, so this, just let me emphasize the vocabulary that you need to. So you need to know more or less what is the Shor lemma. At least this part of the Shor lemma, it's a bit more complete. Then you need to know this Casimir operator. It's quite important in group theory. So in Casimir just means that it's an operator which is going to commute with all the generators. Okay. And then using the Shor lemma, you know this, okay, for a given irreducible representation. And in fact, another part of the Shor lemma which are in the lecture note, but I'm not going to write here, is that you can really use this to test whether a representation is irreducible or not, okay? Because in the case, you can find a matrix which commutes with all the representation matrices of your generators, but which is not a multiple of the identity matrix, then you can conclude that your representation is not irreducible. Okay, so it's a test also. It can be the second part of the Shor lemma is to test if your representation is irreducible or not. Okay, any questions of that? Okay, so really what you have to keep in mind, what are the different steps, okay, to build irreducible representation of a given Lie algebra. So please first find the Cartan subalgebra. Sometimes it's easier to already find what are the Casimir operator for your given Lie algebra. And then build this representation. So for SU2, what you need to remember is that your irreducible representation are characterized by a spin, and a spin j representation is of dimension 2j plus 1. Okay, so you have spin j. And the spin j here, the j appears as the highest weight in your construction. So dimension. And of course, so now if you go at the level, and so your basis is given by this. The basis of your representation space is given by this set of vectors where m can take the value from minus j to j. And then if you go to the level of the group, okay, usually then you will go to the matrix representation. And again, the matrix is going to be represented in the spin j representation, and the dimension, the label here are going to be this. It's also what you call the magnetic number. Okay, in physics, you will see the magnetic number is this M here. So this is for at the level of the group, where this is defined like. But we will come back on this. Okay, some questions here. Oh. Okay, so now I wanted to add something to go back a bit to the group representation theory. Because you see that here, what we have done is for a Lie algebra. And as I said, in the case of a simply connected Lie group, then what you have done for the Lie algebra can be directly translated to at the group level. Okay, but this is not always the case. And I just want to emphasize some vocabulary that you could see in the literature or in some articles, if you're depending on what you're reading. So I just want to give you a bit more vocabulary in the context of the group representation. And also try to give you some idea where you're going to talk about that in your future lectures. Okay, so now it's group theory. Again, so I already give you some notion of group representations. Right? In the context, in the first lecture, when we were just looking at some discrete group, so there is, as we already mentioned, there is really a link between Lie algebra representation and Lie group representation. But this is also really true in the physics. In physics, okay. And how can you see that? Okay, if you remember, so we're using. Why are we studying groups? Is because groups are describing symmetries. And so for a given symmetry, for example, for a quantum system described by a Hilbert space, you know that usually we're going to use a unitary representation. There is a unitary representation of the symmetry group on this Hilbert space. Okay, it's how we motivate why we're going to use group in quantum theory. But this also gives rise, of course, since we have a group, you have a Lie algebra. So this is going also to give rise to a representation of the associated Lie algebra. And usually this is going to define observable for your system. So for example, you know that when you have a rotation symmetry, then usually your observable are going to be your angular momentum. Okay? And these are exactly this J. So these are the generator of your Lie algebra. These are can be interpreted at the physical level as your angular momentum. Then if you have some translation symmetry, this is going to, in space, this is going to give you some momentum as observable. Translation in time is going to give you energy, and so on. Okay, so you see that really when you have a symmetry of your system, then the observable are going to be translated into, usually you're going to look at the associated Lie algebra of your system to find the observable. Okay? And so let's now go back to the notion of representation of a group. And then I'm not sure I will have time to finish, but I will ask you to read the end of the lecture note. It's not very long. It's just that at the end I want to emphasize. So in quantum mechanics, I told you that usually we're interested in unitary representation. And in fact, this can be a bit more complicated in some cases. In fact, you're interested in what is called projective unitary representation. So I'm not sure I will have time to define that. But in case I don't have time, it's in the lecture note, so please have a look, because in quantum mechanics you will not only talk about this unitary representation, but also about this projective representation. So just what is a representation of a group? again, I am going to give you the definition to make sure that everything is clear of a group G on a vector is V. So again, it's a map D from G to linear transformation of V, but you need to have this additional what do you want is that, of course, the representation of a product of two group elements acting on a vector V is also can be decomposed as the action. And this has to be valid for any V. And so when G here is a Lie group, we can really look at homomorphism, okay? That is to representation D. So for Lie group, now your representation D is going to be a map from G to the set of general linear with V is finite dimensional, and GL again is a general linear group, so the group of all invertible linear transformation. Okay, so here this means that here you're considering all invertible transformations. And of course, so if you have a Lie group representation, that's time, I'm not going to call it D because then with the differentiation I'm not going to see anything, so let's call it rho this time. You can differentiate that, of course, to go to the to obtain the Lie algebra representation. That you can call D rho, which is now going to be a map from your Lie algebra to the space of linear mapping. And of course, now the other way around is to start from a given. The other way around, again, is more subtle, okay? So you have to be careful. In the case of, again, a simply connected group, G, then you can indeed start from a representation of your Lie algebra and exponentiate it to get any representation. And this is in the case of a simply connected Lie group. Okay, in the case, of course, where your group is not simply connected, then you can always act with the map, the exponential map, but it's just that usually you won't get access to, you won't have access to all your representation. And and I already mentioned the example of SU2. So here, really from the representation of the Lie algebra are going to be the representation of the group. Then now, if you go to SO3, which have the same Lie algebra, so if you are at the level of the Lie algebra, you're really going to find the same representation here. But then if you go to SO3, then you're going to restrict your attention to only J integer. Okay, so you won't have all the same, exactly the same representation. Okay, so let's find some explicit representation of Lie group without starting from a Lie algebra. So since every matrix group already sits inside the linear group, okay, GL here, this means that matrix group come pre-equipped with a special representation, which is called the fundamental representation. So this means that indeed here, the dimension of the representation is the dimension of your group. Okay? And this is what we call the fundamental representation. So usually, when you write a matrix, you already represent it, and this representation is called the fundamental representation. But typically, a group has many representations, and again, you can. So maybe tomorrow we are going to look at the. You can get new representation from old one by taking, for example, the tensor product. So then we are going to talk about recoupling theory, especially in the case of SU2. So you should have heard already about Clebsch-Gordon coefficient and stuff like this. So this is also quite important, some quite important tools that you will use in quantum mechanics. So tomorrow maybe we're going to spend some time on that. So this really means that starting with two representations, you can take the tensor product now of these two representations and get a new one. Okay? And so tomorrow we'll see how we can do this. Then again, we have the same notion of what is an irreducible representation, looking at if a vector space has some invariant subgroup or subspace or not. And yeah, so in physics, where are you going to see all these irreducible representation of group? It's because so elementary particles, you will see, will be characterized by a charge. So it doesn't have to be the electric charge. It can be the charge that determine how the particle interact with the weak and strong nuclear forces, for example. And then these particles are going to correspond to irreducible representation of the given gauge group. Okay, so really, when you're going to talk about particles in the standard model, in fact, you are going to talk about irreducible representation of your gauge group. Okay, and again, so I don't really want to start that now, but I'm going to ask you to read it. It's really the last page. So first, we motivated in quantum mechanics that a group has to be represented with unitary matrices, but in fact, because we wanted to have this physical information, so preserved, okay, which is given by the probabilities here, and we have seen that if we have an operator U, which is unitary, then this is satisfied. But in fact, what we haven't specified is that it can be also multiplied by a given phase. Okay, or your state can be multiplied by a phase, and you won't see it here. And indeed, in some cases, this phase is important. Okay, and you cannot. And so in these different cases where this phase is important, instead of unitary representation, you really need to work with projective unitary representation. And what are the projective unitary representation? It's really just when you take into account this additional phase here. Okay, and in particular, so you will see that we have different kind of particles. So the fermionic, what we call the fermionic particles, which are in fact all the particles which are interacting, and the bosonic particles are just going to be the force-carrying particles are going to be boson of spin 1. So for example, a photon is a boson. But then all the quarks and leptons in the standard model are going to be fermionic particles. And to describe a fermionic particle, you really need to talk about projective unitary representation. Okay? So I let you.
When you say projective, it means something related to projective space in the sense that you consider that all the vectors that go along some direction are the same?
Yeah, so here it's really in this sense that where you have this additional phase here. Okay, so maybe in the complex plane here you can see something with some direction, but it's really related to this notion of phase. So here, for example, instead of So remember, for unitary representation, you want that the representation of the identity of the unit of your group is the identity matrix. So now you will have that you will have an additional face. Okay? So you have the face entering everywhere, and so then you have this what is called the co-cycle entering in the multiplication law.